All right, welcome back. Just jump right into things. So today we're going to talk about data structures again. We've talked a lot about dynamic set data structures, where you want to maintain a set of elements. And today we're going to talk about a data structure where you want to maintain multiple sets. Finally, we've graduated to multiple sets. This is often called union find, okay? Because with these sets, we want to support two operations, union and find. So let me state the problem. So you want to maintain a collection of sets and one key property of these sets is that they're disjoint. So I'll call the collection of sets script S. This is the way I draw script S. And each of the sets capital S. Okay, so let's say we have, I don't know, R of them. Okay, and we want to maintain them subject to some operations, union and find. But first, I need to say sort of what we care about these sets. So each set has an element distinguished as the representative element. So let's call the set SI. Okay, so you can think of this as the smallest element or whatever. We don't really care much about what this element is. Okay, the elements aren't ordered. There's sort of no structure. There's just elements. Either it's in the set or it isn't in the set. Okay, the sets are disjoint, so any element is in only one set. And every set has a special element called the representative element. Okay, so that's the setup. Reminder that the quiz 2 starts on Wednesday. You have to be here on time. Otherwise, you'll be marked as late for the quiz. Okay, so remind your friends. 9:30 MIT time is the quiz. Okay, so now we want to support some operations. Okay. Simplest operation is sort of insertion. Maybe I want to make a new set with some element x. Okay, so it better be a new element. So I want my x to not be in any of the current SIs. So subject to that constraint, I can create a new set, which is the singleton set x, and add it to my collection. Okay, so in particular, the representative of that set is the element x, because it has to be one of the elements in the set, and there's only one. Okay, we don't allow the empty set. All right, now the more interesting things are I can do a union. So if I give you two elements, say x and y, then I want to find, so let's suppose that element x is in the set Sx, and element y is in the set Sy. So that's just naming the sets that they belong to. It's well defined because the sets are disjoint. Then I want to replace Sx and Sy with their union. okay, in my collection script S. Okay, and that's a disjoint union. And finally, this would all be really easy if we have no queries, right? You don't have to do anything. So what do you want to know about the sets? Well, I'd like to know this representative element. So find set says, well, I'm given some element x. I know it belongs to some set. So let's, again, suppose that x is in Sx. Then I want to find the representative of this set Sx. Okay, which set do I belong to? Sort of what this is asking. Okay, but instead of returning the set, I'm going to return its representative. It's essentially the same thing. You can think of the representative as representing the set. That's why it's called representative. So either I want to find rep Si, I want to find Si. Essentially the same idea. Rep will be, having this representative will be more convenient for designing data structures. Okay, and we want to do this as fast as possible, of course. So there's lots of ways to do it. Some are faster than others. By the end of the lecture, we'll have a really, really fast data structure. So any ideas on how to get started? What's sort of an easy way? What's an easy mechanism for doing this? A very simple data structure where we could just support these operations, spend lots of time. Okay, or a more sophisticated method, whatever you prefer. So it doesn't have to be from this class even. You can take any data structure you know from 6001 or whatever. What's a good way to? What's a way to do this? Not necessarily good. People have to wake up. I know I'm tired. No suggestions? Yeah?
Store a bunch of arrays.
Store a bunch of arrays. Good. Yeah, we could represent every set by an array with all its elements. Okay, that's a little inconvenient, I guess. Because unions, then you have to create a new array. But we could use arrays. We could use we could use linked lists. Okay, essentially the same. Good. So I'm going to say linked lists, but you could do the same thing with arrays. Okay, I can just represent each set as a linked list of all of its elements. So let's call a set Si, and suppose it has elements x1 to xk. Okay, then I'd just like to write it as a linked list. Okay, so this will be my set Si. And I'm going to have a doubly linked list, just for flexibility. Okay, so that's a doubly linked list of the elements in that set. So that represents the set. And I should say what the representative element is. So I'm going to do this for every set. So if I have R sets, I'll have R linked lists. So what should I choose for my representative element in a linked list? Sorry? The first element. Good. So let's just make this the representative. You can make it the first. You can make it the last. Okay, but there's something canonical that we can all get to. Because it's doubly linked, I can find the representative just by walking to the beginning of the list. Okay, one by one. That's easy, but let's just see where we are. So how quickly can we support the operations? So how quickly can I do make set? Okay, this is another easy question. How long does make set take? Order 1. Okay. So if I want to do make set x, all I have to do is create a new node x, which is all by itself. Okay? Because this represents the set just with x. Okay, so that takes constant time. Okay, what about union? How quickly could I do a union? So I'll start drawing the picture. I have some set with a bunch of elements, and I have another set. Now I want to union them. How should I do it? Yeah?
All you have to do is join the tail of one list to another.
Right.
That would take constant, but you have to find out which sets they were first.
Good. Yeah. All I need to do is join the tail of one list to the head of the other list. But I first have to find the tail of this list and find the head of this list. And so that'll take linear time, I guess you said. Good. So this takes linear time. Constant time after I sort of figure out which set I'm in, once I figure out the tail and the head, but linear time nonetheless. And so in particular, to do find set, to find the set that contains element x, that also takes linear time. Okay, so that's the starting point. I mean, at least we can solve the problem in linear time per operation. Okay, not very impressive, but it's a starting point. And we'll use this idea for one of our data structures on the way to what we're doing. Okay, what's a somewhat smarter way? What other data structures do we know that will get faster than linear time per operation? Yeah?
Hash table?
Hash table. Cool. Hash table. So how should I use a hash table? I think hash tables are a little tricky. So you want to represent each set maybe with a hash table. And that way, well, you could just have one big hash table, I guess. And for every element, you quickly hash in. And then there you store what set you're in, I guess. So that would work. And that's essentially that will be our third solution. Okay, but hash table is a little bit of overkill. Okay, I'm assuming that given element x2, I can find where x2 is. And so you could use a lookup table. Given x2, just store the representative element. So you don't need hashing here, but you could do that, and that will be our third solution. Okay, so we'll go there. That's a sort of more sophisticated linked list. Okay, so we'll do that next. But first, I want to get sort of the more obvious ideas. What other data structures do you know? Could I use Venn and de Boas trees? I don't know, could I? They probably won't help me. I don't really have a fixed universe. I don't really have order. Okay, Venn and de Boas trees really need order. What else could I use? I think way back. What was the first data structure we saw? I think it was the first. No ideas, boy. You all partied over the weekend, I guess. Yeah?
You can put them all into a tree.
Put them into a tree, sure. Let's try a balanced tree. Okay, then I should get like log time, right? That sounds good. So I could represent each set by a balanced tree. And maybe the tricky part here is that I don't really have order. Right? These elements are unordered. So I'm just going to throw them into a tree in some arbitrary order. I don't really care whether it's maintained, okay, unlike normal search trees. Okay, so I'm going to ignore the keys. I could throw in arbitrary keys. I could do whatever just to make red-black happy, for example. And what should I choose from my representative element? Okay, again, there's many choices. The root. Root's a good choice, because root is what will extend to future data structures, the root of the tree. You could also choose the leftmost child. Okay, anything canonical would do, yeah.
Is the representative element allowed to change over time?
The representative element is allowed to change as long as you're changing the set. So if I do union of x, y, sort of the representative element has to change for one of the two sets. So here, it changed for y. It didn't change for x. But it's OK. It's allowed to change every time I do a union. The key property I want is that as long as I'm just doing finds, the representative doesn't change. So in particular, given two elements, I can tell whether they're in the same set by running find on one and find on the other and seeing whether that returns the same thing. So that's the property I want. Good question. OK. So now I have my three operations. OK, make set is, again, easy. I just create a new tree with one element in it. So that takes constant time. What if I want to do find set? OK, I guess find set's pretty easy, too. I just walk up till I find the root. OK, so how long does that take? Any suggestions? So I'm given some initial node x. I just walk up the tree from there. So that takes log n, right? Yeah?
The trees are in order, so don't you have to look to figure out which tree x is in and then look at all the nodes?
So the model here is for any element, I can associate some information with it, okay, like node of x or whatever. Okay, but I'm implicitly associating x1 with the node that contains x1. Okay, so I immediately know this node, okay, or if I'm x2, I immediately know this node, and then I have to figure, then I just sort of, I'm in the data structure, I have to figure out where I am in the data structure. Okay, so you imagine you're already immersed in the environment, you just have to figure out where you are. Okay, either you can think of there being a pointer there that tells you, given x1 or x2, the thing in the data structure, or you have a hash table or something. Okay? But you're already given where you are in the data structure. Another good question. This is sort of the model of what's going on. Find set of x gives me where I am in the data structure, gives me a place in the data structure, but I have to figure out what set that's in. Okay, so if I have many trees, all I have to do is walk up the tree, and then I find the root. Okay, and then I sort of know what set I'm in, because I figured out what the root is. Is that clear? Good. Okay, what about union? So if I want to union the set containing x and the set containing y, how should I do it? Now, this is more sophisticated, but you've seen it already. Yeah?
You maybe just put the two trees side by side, and pull the bottom element off of them, stick it at the top as the new.
Cool. That's a good idea. And that's not the one I was thinking of. But yeah, you have two trees. I could take some node off the bottom of one, because I don't really care about order, put it as a new root, and then make the two trees the children of that common root. So that would work. Only trouble is it may not guarantee that we stay balanced. If we want to stay balanced, well, I've got to have logarithmic height, and maybe one tree is really small. And I think that could lead to trouble, right? Because it could be, I could grow a tree in that method by that mechanism that looks something like this. Okay, we're going to actually do that next, so that you're on the right track. But if I want to guarantee balance, how should I do it? Okay, you have to think, so I have a balanced search tree, yeah?
You have insert a bunch of times? Like,
You could insert a bunch of times, yeah. So for every element in the set containing y, I could insert it into the set containing x. And that would take like n log n time at most, right? Probably less. Okay, but I can do better. So what if these are red-black trees? And you have to think back to problem set 6, 7, something, I don't remember. Okay, if I have two red-black trees, and imagine the picture. I have one here. I have another red-black tree. So this contains x somewhere. This contains y somewhere. I want to put these things together so that they all have a common root. So one proposal was to do this. But if I want to keep it balanced, I could concatenate. Right? I don't care about order. So we saw an algorithm, or you developed an algorithm in the problem set for concatenating the set containing x and the set containing y. I know how to concatenate trees. I might as well decide that all these guys are less than all these guys. Then I just want to merge them into one tree and keep balance. So you saw how to do that in how much time? It's pretty fast. OK, you're thinking back too far. OK, study for the quiz. OK, it's coming up soon. This took log n time. OK, the basic idea is you take the smaller guy, you make it a child at the appropriate height, at the appropriate black height over on the left-hand side, and then you might have to do some rotations. But that was, so maybe it took time proportional to that branch. But it was logarithmic time. OK, pretty fast. Good. So this is better than our linear solution. Now we have a logarithmic solution. But it's still sort of what we already know out of the bag. And it almost feels like overkill, right? We're using this balanced search tree structure when we don't even care about searches. All we want to be able to do is walk up the tree to its root. OK, so we're going to use a much simpler idea, like you suggested, that will sort of forget about balance and just merge trees in an easy way in constant time. OK, so we're going to use exactly what you said. OK, but let me first give you an outline of what we're going to do. OK, so this is sort of plan of attack. So this is a preview of what we're going to see. Our goal is to do a lot better than log time, OK, in an amortized sense. So we're going to do a lot of amortization today. And amortize is going to be better than log. OK, so better than log. So one thing you could think of is log log. OK, log log n. Right, we've seen that with Venn and DeBose trees, or log log u in Venn and DeBose trees. But I'm going to do even better. OK, I'm going to even do better than log 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 n. OK, so this is going to be really, really fast. It's going to be better than log 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 n, but not quite constant. OK, really close, but not constant. Still going to be, as n goes to infinity, it's still going to go to infinity, but really, really slowly. Okay, slower than all these functions. Okay, and one cool thing is what that function is, and I'll describe it towards the end. The way we're going to get there is by two tricks. Okay, I'm going to show you two tricks compared to sort of these obvious schemes, or moderately obvious schemes. I'm going to use two somewhat less obvious tricks. Okay, it doesn't really matter whether they're obvious. What's nice about the tricks is that they're powerful. Okay, you can use these tricks in a lot of contexts. And in particular, it solves this problem great. Okay, so each trick gives you a log solution by itself. So it's going to convert a trivial linear time scheme. So like these linked lists, into a log scheme. Okay, so that's sort of neat. You take the obvious sort of brain-dead linear time algorithm, you apply either trick, magically it comes out to log. And it's not obvious that it comes out to log. Okay, that'll be where the amortization comes in. So this is log n amortized. Okay? And the cool thing is that both tricks together makes it really, really fast. So that's where we're going. Now, the first trick will be in terms of lists, but not quite lists as I've given them here, but rather lists as you set them, okay, where you just have a table that tells you which set you're in, which representative element of the set you're in. Okay, the second trick will be in terms of trees, but we'll get there later. So we're going to use everything that we've talked about so far. So it should seem easy so far, but we're going to go. It's not quite as many tricks as we used in Van de Boas. I think there were like 5. Okay, but here we'll just need 2 tricks, and we'll get to even faster than Van de Boas for this problem. Okay, so the title of this next structure is an augmented linked list. Okay, so you can guess what that means. Let's suppose in addition to this linked list structure, which is sort of the most bare bones thing I could have, just storing all the elements together so I know who's in what set. How could I augment that data structure and make it go faster? Okay, so how could I augment, in this context, how could I make this go faster? Let's say I just want finds to go faster. Okay, currently they take linear time. Yeah. Right. For each node, I could have a pointer to the representative element. So if I have my list x1, x2 to xk, and they're already linked in so that I can at least traverse them. In addition, every node could have a pointer to the representative. Okay, so these are representative pointers. Okay, then my finds take what? Constant time, right? Because I just have the answer right there. If every node stores a pointer, well, then it knows the answer. It knows what the find of that element is. So let's call each node x. Then it stores the representative of x, which is the representative of the set containing it. Okay, which we called Sx. So that's easy. So find takes constant time now. How long does union take? So what does union do? I mean, that's the more interesting thing. Now what do I have to do as a union operator? Yeah?
Well, the thing is, after you do the union, you're going to need to take whatever the second set is and reset all of their representative pointers.
Right.
New
Exactly. So if I have 2 sets, I'm going to, for whichever one I change the representative on, I'm going to have to update that pointer. So if I have some y1 to yj, okay, same picture is up there. And now I want to do this union. So we know how to do it in terms of the original linked list. But now we have these representative pointers. And initially, the representative pointers all go to y1. Okay, but for the union, I want to update all of these pointers to point to x1, because that's my new representative. Okay, this is poor man's color chalk, right? These are the new pointers. I'm going to erase these ones and replace them with these dotted lines. Okay, that's what I need to do. That's just to maintain the augmentation, to maintain this new information. So it takes linear time. Seems easy enough. So that's an easy solution. This is the trivial linear time solution, and now we want to improve it to log. So, yeah.
Do you have to worry about like duplicate elements so that like if the two sets each have an element in common, you have to eliminate it from one of the sets?
Yeah, you should worry about it. So the question is, should we worry about duplicate elements? They would break everything I'm going to discuss. Okay, I mean, you could fix them in the sense that you could check for them and then report an error. But all of this is going to assume that there are no duplicate elements, that all the sets are disjoint. Okay, because they'll break otherwise. So if you're going to implement this, you should check, does this element already exist, or is it already put in the data structure? Because then there'd be trouble. Right. Okay, but
Or make set just creates.
right, or make set makes a totally new node which can store your key or whatever. But the nodes could be represented by the data structure itself. So they don't really exist. All right, so make set could return the new node that you create. And that's your element. And you'll be guaranteed that you'll never put that in another set. So I guess one thing is that when you union two sets, you should check that they're actually different sets. Okay, these are all sort of you want to check your preconditions. But I'm going to assume that all of these hold. Okay? Good. So that's then all we have to do for a union under those assumptions. How could we do better? Let's suppose that the set containing X is really small. Okay, maybe it only has like 2 elements. And then what I have to do is, again, update these pointers. But that's somehow very quick. What costs me is updating. So I have, to link the two lists together, that's quick. What costs me is to update all of these pointers. So what could I do in this scenario that would be faster?
You add the X set to the Y set.
Right. You add the X set at the end of the Y set instead of the Y set to the end of the X set. Okay, seems like a trivial observation, right? But that's trick 1. Okay, so these are not hard tricks, but they're powerful ones. So the idea is, well, I mean, what should I do in general? See, what was bad here is the Y set was really big, and the X set was really small. So I should really put the X set into the Y set. So I should just put the smaller set into the larger set. Okay, that's trick 1. Take the smaller set and merge it into the larger set, as opposed to the other way around. And update the pointers only for the smaller set, not for the larger set. Okay, it seems easy. So what do I want to say here? Okay, so let's suppose, this is, again, a concatenation operation. But for linked lists, concatenation is very easy. It takes constant time once I know the ends of the list. Once I know what list I'm talking about, I can concatenate them. So you take the list with the fewer elements and concatenate that at the end of the list with the more elements. Okay, so how long does this take? How can I write it just concisely how long this is going to take? Okay, I've got to update all these representative pointers. The concatenation is quick. It's the augmentation, all these Y pointers or the X pointers that takes me time. So how can I write that? This is sort of a modeling question. I mean, it's certainly at most linear time. But how can I represent that this is somehow doing a little better? Yeah. Sorry? The minimum of the lengths. Yeah, good. Okay, so this time is proportional to the min of the size of set Sx and the size of set Sy. So it's just proportional to the smaller of the two sets, okay, as opposed to the larger, which is, or the sum or whatever. So this is capturing that we're doing faster. Okay? Yeah?
Would it be beta n to find the size of the list?
To find the size of the list. Good point. So we have to augment, again, to store the size, because otherwise it would take too long. Yeah. I'd have to spend linear time just to find how long the lists are, and then I'd know which one's the smaller one, and then I could do what I do. But I should first augment each list to store its size. Okay, we'll call that the weight of the set. So the weight of SI is the number of elements in SI. Okay? So we can store that at the representative element, for example. So once I do a find, I get the representative element. Then I can look at the weight field, and that tells me how long the list is. And then I know which one's the smaller one, and then I do the appropriate concatenation. Okay? So then it will only take this much time, plus a constant. But I'm assuming these are always at least 1. Okay, so very simple idea. What's cool is that it comes out log n amortized. Okay, in the worst case, of course, this could still be linear. Right? Could be both sets are really big. But in the nice cases where one set is smaller than the other, it's really fast. Okay, and magically, I mean, there's sort of no logs going in here, but it ends up log. Okay, so that's the theorem. I need some notation. So this is global to everything we'll see. N is the number of elements. So that's what I've been talking about. Another way to say that is the number of make set operations. Because that's how I get elements into the system. Okay, but in addition to the number of elements, I care about how many operations there are. Okay, I might only have 10 elements, but I do lots of finds. I could do as many finds as I want. Okay, so that's going to contribute to M. It's the number of operations total. So that includes make sets, so it's at least N. It also includes find sets and unions. Okay, in particular, F will denote the number of find sets. Okay, so this is just so we know what we're counting. Okay, these are the easy things to count, and we want to analyze our algorithms in terms of them. So I just want to fix notation there. And now, so let's go here. Now we get to do analysis. Okay, so let's prove that this is log n amortized. Okay, it's sort of log n amortized. If you do lots of unions. So the point here is that finds are fast. If we can do all this augmentation where we know, from every element what the representative element is, well, finds are constant time. Make sets are constant time. All that costs us is unions. So what we care about is the cost of all the unions. So I want to amortize things out. I want to look at all of the unions. And their total cost, I claim, is order n log n. I think I should be, that's it. Okay. So that's good if I do lots of unions, right? If I do order n unions, which is at most how many I can do. If I create n sets, each time I union them, there's no way to split them apart again. So I can do at most n minus 1 unions. Okay, so that's a little observation. Can't have too many unions. On the other hand, we might have very few unions, and then this isn't such a good bound. Okay, because it's sort of saying, well, suppose I had n unions, then it's at most n log n time. Okay, but that's what we'll prove. And usually you want to take unions until you have one big set that contains the whole universe. And so this is the bound you want. Okay, so let's prove this theorem. So there's something involving the number of elements. So let's just fix a particular element of interest. Okay, so let's say we monitor a particular element. Okay, call that element x. And we're also going to keep track of the set that contains that element x. So again, we'll call that S sub x. Okay, so these are things we can keep track of. And what I care about is how many times the rep of x, the representative, pointer changes. Okay, that's what I want to count. So I'd like to prove that that's at most log n. If I could prove that that's at most log n, if I add it up for every element, then the total is at most n log n, because there's only n elements. Okay? So that's what I claim the answer is, and that's what you can sort of guess at this point. The question is, why? Any ideas why? So this is getting a little trickier. Where does the log n come from? Yeah?
Well, like when you move, when you merge two sets using union, you're sort of reducing. You get rid of two sets, but rep only changes like for one set. So if you were to do a whole bunch of merges, like you're sort of doing like a divide by two kind of thing. So.
Kind of doing a divide by two kind of thing, exactly. Because when I have two sets, I only change the reps in one of the sets, and I've reduced the number of sets. So that seems like progress. So what if I look at just this particular element x and the set containing it? So it's a question of when the set merges with someone else. So let's say, each time Sx merges with someone. So I guess because we're talking about unions, the appropriate word is unites. Okay, so each time Sx unites with another set, let's say Sy, okay, then we're sort of making progress because only Sx or Sy has its rep pointers changed. Now here I just care about x. So I just care about when the pointers in Sx changes. Okay, that's sort of the simplifying point of view, if you will, from the proof. Okay, really I care about all of them, but I'm only going to concentrate on one element x at a time. So when do the pointers here change? The rep pointers from all the elements in Sx. Right, if the length of Sx is smaller than Sxy. So there are two cases. First case is Sx is the smaller set. Okay, maybe even smaller or equal. Okay, then we pay 1. We pay 1 to update rep of x, this particular element we care about. Okay, so that costs us something. We like to charge that cost to something else. So what's good about this situation? This is actually a good situation for us if Sx is smaller. I mean, it better be. Otherwise, we'd have nothing for this to pay, to charge to. So what's good? Again, we're monitoring x. We're also monitoring Sx. So what changes about Sx? Yeah? The length of it at least doubles, exactly. Okay, that's the good thing. The size of Sx at least doubles. This is where the log is coming in. Okay, because it increases by the size of Sy, right, because they unite. They're now one set. And we know that Sy is at least as large as Sx, so the total size at least doubles compared to what Sx was before. So that's good because set sizes can't double too many times. If you start at 1, when you do a make set, it starts at size 1. It can get at most size n because there are only n elements. If you're doubling each time, that's at most log n. Okay, that's where the log n comes from. Okay, except we have one more case to do. Okay, but it's not a very exciting case. Maybe you can see that already. The other case is when it's sort of an easy case. Sx is bigger than Sy. Then what happens? So this is sort of harder for us because now Sx may not be doubling in size. Sy may only have one element. We're just adding one element on. So there's nothing really to charge to. But why is that okay?
You don't pay anything.
You don't pay anything, right? 0, okay, for x. Okay, so we're just monitoring x. Here, x, the rep of x doesn't change. So we're saved. We don't have anything to charge to, but we don't have anything to pay either, so we're OK. So you can double at most log n times, and so we're done. Okay, that means that there's a log n cost for each element x, for any element x, and there are n elements, so the total cost is at most n log n, no matter how many unions you do. Okay, and that's what we wanted to prove here. Is that proof clear? Okay, this is kind of surprising, I think, that just this simple idea, this simple trick gets you a log n solution. But we need more tricks, because that's not sufficiently exciting. So the next idea will be that we'll go back to trees. Okay, so this was a simple way to do trees in the sense that we just used all our infrastructure that we knew how to do. Right? We said, well, let's make them balanced. We'll use red-black trees. Okay, it's overkill, but then we know how to concatenate them, do everything in log n time. But we'd sort of like to do faster, or at least simpler. Okay, so let's do trees. So I'm going to use a slightly different representation than this one. But I want to keep the essential features. One essential feature is that the representative is the root. Okay, that seems like a good thing. But balanced tree and ignoring the keys, that's sort of bizarre. So why don't I just say it's a tree? I don't really care much about what the tree looks like. So, because all I want to do is be able to find the root. So in fact, I don't even need child pointers. All I need are parent pointers. Okay, that's sort of simplifying to me. So we'll represent our set Si, every set Si, as an unbalanced tree. Let's see. I want lots of adjectives. It's unbalanced. It's unordered. It's, I don't know, what other good, I think I have one more word I'd like to apply. Non-binary. Okay, it doesn't have to be binary. Because all I need to do is go up in the tree. I don't care about going down in the tree. So why not make it non-binary? Each node can have as many children as it wants. Okay, it's like a free society. Cool. So I won't give the tree a name. And furthermore, I want so each node is only going to store parent pointers. Okay, we'll augment it with other stuff, but in particular, it doesn't store child pointers. So that's what we're going to do. So let's say I go. Actually, I'm going to want trick 1, so I'll go somewhere else. Let's get rid of this old tree solution. So let's suppose I have some set Si, and it has, I think, 6 elements. And I'll just match the notes here. So we have some x1. Let's say x4 is down here. It's completely unordered, so I don't really care where I put things. Okay, and each node is storing just a parent pointer. Okay, so that's a simple, this is x6, a simple 6-element tree. Everyone stores a parent. You can have as many children as you want. It might just be one child. Okay, I might just have someone hanging off here. Okay, it's arbitrary. And it's not balanced. And so the question is, how do I do the operations? So make set, again, is easy. Make set, I just create a new node. Its parent pointer is nil. Okay, the interesting things are find set and unions. So how long does find set take in this context? So again, I give you some node x in the tree. You've got to find the root. Okay, I didn't mention it, but the representative of Si is, again, the root of the tree. Less than logarithmic? Because you have more than 2 children. Actually, I may not have 2 children at every node. And furthermore, it could be I have this tree, okay, which I drew earlier on. So even though every node has 2 children or it's a leaf, it may not be balanced. Okay, so that's a bit of trouble. It's not actually logarithmic all the time. Okay, like I said it. Yeah. Order of the height. Yeah, exactly. That's what I want. Because this captures, it's proportional to the height of the tree. Actually, in fact, it's proportional to the depth of x. Okay, as long as I define depth to be at least 1. So this is a slightly tighter bound. In particular, it's at most n. Okay, 'cause it could be linear. Okay, and in fact, this is only a linear solution. Okay, but we're going to make it better. So this is just a very simple thing. It could be to walk up to the root takes linear time. Okay, kind of sucks. But now, what should we do for union? Okay, we've made our life more difficult for find set. So maybe we could do unions faster. So how should we do unions? Yeah.
You just set the parent pointer of the root to summon.
Right. So if I have another tree over here, say y1. Okay, I'll match the notes again. 4, 3, 2, 5. See if I can remember them all. I just have to set the parent pointer of the root of this tree, or one of the 2 trees, to be any node in here. Because if I do that, and I do find set from any of these nodes, it will walk up, it will get to its old root, then it'll follow the parent pointer, so it'll go somewhere in this tree, and then it'll walk up to the root here, and it finds the root of the whole tree. That's what I want. Okay, so to make our life a little bit easier, why don't we set the root of this guy to be have parent the root of this guy. Okay, so that's what I'm going to do for union. I'm going to say, well, I'll find the root in the y tree. Okay, I can do that using find set, which takes linear time. Okay, but suppose we could do find set faster. Then it's just one operation we need to do. Take find set of y, set its parent to find set of x. Okay, as long as we could do find set faster, this will go fast. It's only constant time plus 2 find sets. Okay, so that's some progress. With the old trees, we had to spend logarithmic time. Now we have potential to get faster. Okay, constant time, if we're lucky. Good. So one thing we could do is use trick 1 again. Okay, trick 1 works in this context as well. Instead of storing direct pointers, we can do a simpler thing with these trees. Okay, actually, why don't I use the trick 1 board? Okay, instead of concatenating the smaller list into the larger list, I'm going to so instead of this, I'm going to do this sort of merge with the smaller tree. Okay, I'll merge the smaller tree into the larger tree. You see, what I'm paying to do a find is the depth of the node. So I want to keep the depths of nodes as small as possible, ideally like logarithmic or something, or better. Okay. The ideal picture, of course, is that I have this tree. Right? That would be great, because then this is like the simple linked list. Everyone stores who its representative is. If I could get to this picture, I'd be home free, because then it's constant time to do a find set. So that would be good. I want to minimize depth. Here, all the depths are like 1 or 2. Okay. Now, here I have a choice, right? I could merge y into x, and that increases the depths of all these nodes, because they now have one new node above them. Or I can merge x into y, and then all the depths here increases, and the depths here stay the same. Okay, so I'll do the smaller one into the larger one. That seems like less work. Okay, smaller and larger just means how many nodes you have. So again, you have the weight of a tree. And that's just the number of nodes. Okay, so I'll take the smaller weight tree, put it into the larger weight tree. Easy idea. Again, we can prove that it's logarithmic. Here it's even easier. So this is trick 1 again. Good. So the point is, so I claim that, okay. I'll do the proof first and then the claim. It's somehow easier. Okay, you want to look at the depth of a node. Right? When does the depth of a node increase? Well, if you focus on node x and you focus on the set Sx containing it, the depth of a node will increase only if it's in the smaller set. Okay, that means that the other set was bigger than this one. And so the size of my set doubled again. Okay, so that means that the depth of that node can increase very many times. Okay, so it increases only when, let's say, x, size of the set containing x, doubles. And so that means the depth of a node is logarithmic in the size of the set. Okay, that's the cool property. So that's depth of a node. That's also like height of the trees, right? The height of the tree is just the max overall depths. The point is now the height of a tree is logarithmic in its weight, in the number of elements. Okay, so that means the total time taken by this data structure. Okay, that means if the height is logarithmic, that means that the depth of every node is logarithmic, so find set takes logarithmic time. Unions take constant time. Right? As long as I augment to store the weight, I can do this in constant time. So this is progress. We've actually improved somewhat over our linked list structure. We have the number of operations. You've got to spend at least that much time. And then for every find, it takes log n time. Okay? This doesn't even have to be amortized. Okay, it's even true that finds are worst case log n. Okay, but I'll state the amortized bound because all of my other bounds will be amortized. Good. It's time for the second trick. Okay, where should I go? So let's see if you can guess what the second trick is. Okay, if I do a find, so the idea is, well, unions can't be much smarter than this. So maybe finds could be smarter. Okay, they've got to walk up the tree. But it's sort of wasteful. You know, if I do find on y2, okay, let's just suppose I do find set of y2. Well, I walk up to y3, and then I walk up to y1, then I walk up to x1, and then I walk up and I say, oh, there's no parent. That's the root. Okay, and I visit these 3 other nodes. And if I do find of y2 again, I have to visit the 3 nodes. And if I do find of y2, I have to visit the 3 nodes. How could I make that faster? Yeah. Yeah. When I do a find of y2, I can change what its parent is. I can say, well, I mean, I don't really care who my parent is as long as I get to here in the end. So now that I've done the find, why not change the parent pointer directly to x1? Then next time I do find of y2, it's fast. It's constant time. Okay, as long as I don't do more unions. If I do more unions, it'll get slower, but it won't get slower too quickly, to put it strangely. So that's good for y2. But now if I do y3, I still have to visit all these nodes. So how can I make this even better? And this is maybe a little trickier. That's why it's called trick 2. Okay, what should I do? Yeah?
Just update the parent pointers of all the nodes.
Update the parent pointers of all the nodes on the path to the root. Right. So I could change the parent pointer of y3. And I could change the parent pointer of y1. Well, y1 already points there directly. Okay, so I could take all of these nodes that I visit and change their parent pointers, because I'm visiting them anyway. It takes me time proportional to the length of this path just to go up it. After I go up it, why not say, oh, that's the new root. So why don't I set this guy's parent to the root, this guy's parent to the root, and this guy's parent to the root? That makes my tree shallower. It's decreasing the depths of some of the nodes. Not only does it decrease the depths of these nodes, it also decreases the depths of their descendants, of all their children. Right? So y5 now has depth 2, whereas it used to have depth 3. Okay, or I'm getting off by 1 errors, but it went down by 1. Depth went down by 1. That's safe. Good. That's trick 2. Okay. It's called path compression. Because I traverse some path. It may be very long, but once I traverse it, I know what the right answer is. So I can just compress that path into a tree that looks like this. So this is actually the picture. That's sort of coincidence. I didn't intend this to happen. Okay, if I do a find here, I visit all of these nodes, and then I'll make all of these nodes children of the root directly. So it converts essentially into this, except each guy has one hanging off. Okay, I can make it easier by removing these nodes. Okay, this is just reusing pictures. It's kind of fun. So now all of these guys, okay, I better start here. They all become children of the root. Okay, and that's good, because this is when finds are fast. So if I keep making these transformations, every time I do a find, that's trick 2. Okay, this is a very useful idea. I mean, you can use this in many contexts. When you're dealing with any kind of structure where they all want to find, essentially they want to find the root, but the root might be changing on them. So they'll kind of try to keep track of where the root is, but they might be off by a little bit. What's nice about this structure is if you're off by a little bit, that's still useful. I might find this root, but then it's very easy for me to get to the true root. I've made a big step by going here. And that's what these parent pointers are doing. They're giving me an estimate of the root. Okay, that's path compression. And it's time to analyze it. Okay, maybe I should write it down first. That's always good. Okay. So find set, we're changing find set as opposed to union. It discovers the representative element. And not only does it discover the representative element for x, but it discovers a representative element for every element in that set. Okay, in particular, for all the nodes on the path to the root from this node x. Okay, that's potentially a lot of nodes. That's how much it costs. Okay, so why not set? So path compression, we're going to make all of these nodes direct children of the root. Okay, easy enough. And the point is the cost of this find is still proportional to the depth. Okay, we haven't made it worse, because it only takes twice as long to visit all those nodes again. And now we'd like to show that amortized, it does a lot better. Okay, and this is where I'm going to, and I only have 15 minutes left. Okay, I'm going to prove that trick 2 alone gives me log n time. Okay, trick 1 we know gives you log n time. Trick 2 I claim also gives you log n time, even without trick 1. Okay, so this is trick 2 alone. I guess this lecture would have been really appropriate around Halloween, right? Except there are no treats. Well, I guess there's a treat at the end. All right. So unions are constant time. Make sets are constant time. All I care about is find sets. So the total find set cost is basically n log n, except it's m log n. Okay, because for every operation I might spend, I'm doing many find sets. I might do up to m of them or f of them. Claim it's at most log n amortized each. Okay, and this will be a fun amortization. This proof is not in the book. And it took me a long time to find a proof, or to come up with a proof. I couldn't actually find one, because I didn't want to cheat by looking it up in the library. So here's my proof. I'm sure this is known. Okay, I'm going to use a potential function. See, the tricky part is unions can do a lot of, in coming up with a potential function, unions make things bad, right? They take maybe two really big sets and merge them together. Any sort of obvious potential function like summing up the depths of the nodes, that was the first thing I tried. Okay, that's bad because a lot of the depths go up. So I couldn't figure out how to make that work. Okay, but what does work is if you look down instead of looking up. Instead of looking at the depths, which is how far down they are, look how far up they are, I think. Yeah, in some sense. Okay, so I want the notion of the weight of a node. Okay, we've seen the weight of a tree. The weight of a node is the number of descendants it has. Okay, the number of nodes in that subtree. So if I pick some node x, it's the number of nodes in the subtree rooted at x. Okay, and then my potential function is going to be the sum of the logs of the weights. Okay, so suppose that all of my elements are x1 to xn. Okay, in all the trees. For each one, I can compute its weight. I can take the log, and I can add them up. That's my potential function. So what do I claim? Let's look at unions first. That's sort of the easy and less relevant component. So if I union xi and xj, it's going to increase my potential, because unions sort of make the tree look worse. Okay, because I take two different trees, which may look very good, and then I stick them together in a sloppy way. But in fact, it doesn't change the potential of too many nodes. Okay, if this is the tree, so in here is xi, and in here is xj. And let's say this is a smaller tree. I add in this edge, this pointer. Okay, nothing down here changes. All the weights of the nodes are the same. All the weights of the nodes in here are the same, except for the root. The weight of this node goes up by the weight of this node. Okay? So it changes the weight of find set of xi. Yeah, let's say xi. Okay, remember, this is trick 2 alone, so I'm not putting the smaller into the larger. I'm just going to put the second set into the first set, okay, blindly. I claim it's still logarithmic. Okay, it increases it by the weight of the second tree. So that's the weight of the root of the second tree, same thing. Okay, well that's sort of okay. In logarithm, I'm increasing the log of this potential, the potential of this guy, the log of the weight of this guy, by at most the log of the weight of that guy. And that's at most log n. This is at most n. Right, so log of it, so the potential goes up by at most log n. Okay, so that's okay. Log n is what I want to prove. Okay, this just means goes up. So we're almost done. We just have to analyze fine set, okay, which is the interesting part. Somehow I claim that with this second trick, fine sets just get faster and faster at such a rate that amortized is all log n. Okay, the first one might cost a lot. It might cost linear. Okay, but amortized is okay. So let's look at fine set of some xi. Okay, this is the key observation why you care about weight. Okay, it makes a bunch of steps. Okay, it works its way up. I don't know why, but I've called them steps down. I guess that's when you're finished. All right. So when I do a find, I've lost all my trees. So let me draw another one. Here's a tree. When I do a find here, I follow some path. Okay, I'm just going to turn that path around for analysis. Okay, instead of saying, okay, I went up, let's think of myself going down. When would I go down? Okay, I start at some node. I start at the root, and I make my way down towards the node that I care about, just for analysis. Okay, I can't actually do this in the algorithm because I only have parent pointers. Well, I want to split this into two cases. Okay, there's sort of the good splits. There's the good directions. So suppose what I care about is weight. All right. Sorry. I haven't quite oralized this proof before, so I'm trying to think of the best way to say it. Okay. When I make a step down, it's improving the weight. It's decreasing the weight because I make all of these nodes direct children of the root. Okay, what does that do? Well, it takes each of these nodes. They used to be in this subtree, but they're not anymore. Okay, this node used to be in the subtree, but I move it up so it's directly here. So it's now in its own subtree. Okay, this is gone. So the triangle no longer includes this guy. Well, that's good, because that decreases the weight of that subtree. That's all I want to say. Okay. It moves this child C out of the subtree of this parent P. Okay, and that decreases the weight of P. Except for the very first move. Okay, that's what I need to add. So the very first step that I make doesn't improve anything, because I set the pointer of this guy to the root. That's what it was before. Okay, but every other step down is making the weight go down because of this. So in particular, and this is the key observation, if I have a really heavy tree in the direction I didn't go, well, then I'm making progress. If I go to the smaller half, I've reduced the size of the tree in half, okay, that I care about. So that's at most logarithmic. So this is sort of two cases. And I claim that one case can't happen very, very many times. You'll see why this is useful in a moment. The next line. Okay, but in particular, the weight can't go down by a factor of 2 more than log n times. Okay, big deal. the cool part is if it doesn't go down by a factor of 2, then I'm making progress in a different sense. So if the weight of my child is at least half the weight of the parent, it might be the entire weight minus 1. Okay, it might be really big. Well, then I'm doing something good because I'm decreasing the weight of P by this much because I'm taking C out of P's subtree. Okay. So that means the weight of P goes down by a factor of 2. And what I care about here is log of the weight. So that means the log of the weight goes down by 1. So the potential function goes down by 1. Well, that's good, because that's what I needed to pay for. Okay, I'm paying for these steps. The cost of my algorithm is proportional to the number of steps. So if my potential function goes down by 1, then I can use that potential for paying for this step. Great. These steps I don't really have to pay for because there's only log n of them. Okay, so that means that, and the unions only take log n. So the total then is log n. All right, that's all right for the proof. Now, I have a few more minutes, and I want to tell you what the bound is if you have both tricks. Okay, I'm not going to prove it because I don't have time, and it's a really messy proof. Okay, but you should know the result. Because the result is very cool. So I've always been talking about trick 1 or trick 2. Suppose I have both tricks. Okay, then the theorem is that amortize, each operation takes alpha of n time. Okay, but I haven't defined alpha, so it's not a very exciting theorem yet. Okay, so this is amortized, each operation is alpha of n. In total, it's the number of operations times alpha of n. The question is, what is alpha? Okay, and probably I should start on another board. Okay, alpha is called the functional inverse of Ackermann's function. So I'm going to define Ackermann's function, which is called capital A for Ackermann. And alpha is going to be the functional inverse. Okay, so I might as well write it down. So alpha of n is the minimum value of k, let's say, such that Ackermann's function, this is what Ackermann's function will look like, is at least n. Okay, so Ackermann, capital A, is going to be a really fast-growing function. And this is sort of how big do I have to make the parameter till I get n. So that's the inverse. This is like defining a log in terms of exponents. Okay? So if A grows really quickly, then these k's will grow very slowly. Okay? That's the claim. And so here's the really fast-growing function. Okay, and then we'll look at its inverse. So ak of n, is that reasonable arguments? Okay, I'll use ak of j. I don't want to confuse it with that n. Okay, the base case is when k equals 0, and then it's the increment function. And otherwise, it's this magic. Okay, so k and j are integers. A sub 0 of j is the increment function. A sub 1 of j says, well, I'll take the previous function, a sub k minus 1, and I'll iterate it j plus 1 times. So I'm going to take this function and do it j plus 1 times. So what function is that? If I take a number, I add 1 Then I do that, j plus 1 times, this is just arithmetic, 2 times j plus 1. Yeah. Okay, so I'll say, well, that's like the doubling function. I double j. So that's sort of, that seems to be growing pretty quickly, right? I've started from increment, now I have double. All right. What's a sub 2? If I'm doubling every time, then I iterated j plus 1 times. That's roughly, so I start with a number j. That's what this is saying. Then I apply this function, j plus 1 times, to that value. Okay, it takes a while to wrap your head around this definition. But what function is this? Roughly. If I double, I start with j, and then I double j plus 1 times. So that's 2 to the j plus 1. So just think of this as very roughly 2 to the j. Wow, powers of 2. Okay, that's just a sub 2. Okay, a sub 3 is really, really big. Okay, you might think, oh, a sub 3 is like, I don't know, 3 to the power. But no, it says you take 2 to the j, then you iterate that j plus 1 times. Okay, so I'll write it over here. A sub 3 of j is roughly 2 to the 2 to the 2 to the 2 to the j, where there are j plus 1 2's there. Okay, this is a really quickly growing function. Okay, and it's only a sub 3. Okay, a sub 4, I mean, I can't even write down a sub 4. It's just so big. Okay, it says, well, take this. This function is called tower, 2 to tower j. Actually, it's a little bigger than that. Okay, but this is bigger than 2 tower j. Okay, 2 tower j, we just have a 2 up here. It's even bigger. You put a j up there. Okay, a4 of j is saying, take this humongously growing function, tower, apply it j times. Okay, there's really no good notation for that. Okay, that just grows really, really, really fast. Okay, and I mean, this just keeps going. Okay, you get, I mean, with using composition and just iterating these functions, you get really, really big functions really fast. Okay, already at 3, I'm sort of beyond notation. I need to use dot, dot, dots. Okay, alpha is going to then be really small. Okay, so alpha says, well, I want to look at a sub k of 1. Okay, so let's just do that very quickly. A sub 0 of 1 is 2. Okay, a sub 1 of 1, well, that's like twice the number. I'll be precise here. And it turns out to be 3. Okay, I've been rough, so okay, that one's written there. And then I started getting rough. Well, it's around 2 to the j. Okay, in this case, it's 7. Okay, a sub 3. I mean, this looks like a pretty slowly growing sequence, but it starts to grow really quickly. Like, oh, well, now it's like almost a power of 2. Okay, seems like it's growing fast. Okay, but it grows really fast. Okay, a sub 4 of 1, I can't even show you. Okay, I mean, it's just so big. I don't know how to comprehend it. It's bigger than 2 to the 2 to the 2 to the 2 to the 2047, where there are 20482's. Okay, how big is this? I mean, this is just beyond my comprehension. Okay, you can think of this number. Okay, this number I understand. 2 to the 2047. How many particles in the known universe are there? Who knows? Sorry? 10 to the 40th. Actually, that's pretty weak. I think it's around 10 to the 83. Okay, at one point I asked NASA, how many particles in the universe there are? They had this Ask NASA webpage. Okay, it's about 10 to the 83 if you include all the dark matter that they can roughly estimate, and you double count for protons and neutrons or whatever. Okay, this is a big number. Okay, 83 digits. This is around, I mean, this is a little bit smaller than 2 to the 256. That's how I remember. It's like 2 to the 263, I think. Okay, this number is way, way bigger than even this, okay, than the number of particles in the known universe. So alpha is basically less than 4. Okay, it's gonna be 4 as long as you get above 2047. It's not gonna go to 5 in this world. Okay, it still goes to infinity. Because this is growing quickly, but it still doesn't grow infinitely fast. So alpha, the inverse, is still going to grow a little bit. Okay? But this number is just so big, you'll never get beyond 4. So that's the cool theorem. I don't have time to prove it. It's messy. It's in the text if you want to read it. It's cool stuff. And that's union find. Don't forget to be on time for the quiz on Wednesday, 2 days from now.